This program is brought to you by Stanford on iTunes U at Stanford University. Please visit us at itunes.stanford.edu.
Tonight we're going to see how that principle of action leads to a principle of energy and energy conservation. But before we do that, I want to clarify, no, why quibble? Not clarify, correct something that I said last time. At the end of the hour, at the end of the 2 hours, I tend to get tired and I make mistakes. I made a mistake last time. It was a linguistic mistake more than anything. I said something was Coriolis. I meant centrifugal, or I should have meant centrifugal. Let me go back and just do correctly the motion of a particle in a plane described by a radius, a distance from the origin, and an angle. Do it correctly and get all the pieces, which I sort of did a little bit hastily last time. Again, the rules of the game are begin with the system you're interested in, find the coordinates, or not find, but a combination of find and invent a set of coordinates to describe the system. Write down the kinetic energy, the potential energy. That gives you a Lagrangian, gives you an action, and from the action you can derive the Euler-Lagrange equations of motion for those coordinates. So, for example, for the particle in 2 dimensions moving around on a plane, we can describe its location by 2 coordinates. We could use x and y, of course, or we can use r and theta, distance from the origin and angle from the horizontal, for example. Then the components of velocity, now we could choose to describe the velocity by the x and y components of velocity, but we can also use the r and angular components of velocity, the component of velocity along the radial direction and the component of the velocity perpendicular to it, to describe the velocity vector. Right? The component of the velocity along the radius vector, that's just, let's call it v sub r, and that's just r dot, the time derivative of r. The other component, which I can call v theta, let's call it v theta, it means the component of the velocity in the direction perpendicular to the radius. Right? That's not theta dot, but it's r times theta dot. Why? Because a given rate of change of the angle will correspond to a larger velocity the further away you are. Okay? A given angular rotational velocity, theta dot, will give you a larger overall velocity the further away you are, proportional to r. So these then are the components of the velocity in the 2 directions, r and the perpendicular direction. If you choose components of the velocity along perpendicular axes, then the square of the velocity is just the sums of the squares. Sums of the squares of the components of velocity are the magnitude of the velocity vector, and the kinetic energy is just 1/2 the mass of the particle times Vr squared plus V theta squared. So that just becomes r dot squared plus r squared theta dot squared. Now, just to make it more interesting, I also imagined that there was a potential energy, but in particular a potential energy which only depends on distance from the origin. Now, that of course is not a law of thought. You could imagine potential energies which depend also on the angle, but it's especially interesting in many contexts to study the central force problem. The central force problem is the one where the force points toward or away from the origin and is equivalent to the statement that the potential energy only depends on r and not theta. So let's subtract off minus u of r. That's not the energy now, that's the Lagrangian. All right, let's work out Lagrange's equations. Let me remind you what they are, the Euler-Lagrange equations. I'll write them in a general context first. We first construct the derivative of the Lagrangian with respect to the time derivative of any one of the coordinates. Let's put this qi. Let's pick one of the coordinates, call it qi. No. I'm specializing to the special case where u only depends on r. As I said, there's nothing holy about that, but for example, it is true of gravitational forces, the force of the sun on the earth, the potential energy is only dependent on the distance from the sun. It also corresponds to a symmetry, corresponds to rotational symmetry, that the potential energy does not depend on the angle, is simply a statement that the physics of the problem is invariant under rotation of axes. Okay? And we'll come back to that. All right, so for each coordinate, in this case the two coordinates are r and theta. For each coordinate we begin by writing down the canonical momentum conjugate to the coordinate. That means the derivative of the Lagrangian with respect to the velocity, or with respect to the q dot, okay, with respect to the time derivative of the coordinate, and that's called pi sub I. And one says that pi sub I is the momentum conjugate to q sub I. Then the Euler-Lagrange equations are that d by dt of this object, d by dt, sometimes I'll write just dl by dq dot, and sometimes I'll just write pi sub I. Let's write pi sub I is equal to the derivative of the Lagrangian with respect to q sub I. We could also write this as d by dt of the derivative of the Lagrangian with respect to the ith generalized velocity, q sub I dot. That's what we got from the principle of least action when we applied Euler-Lagrange method to it. So let's work that out now for the two coordinates r and theta. First r. All right. The derivative of the Lagrangian with respect to r dot, well, r dot only occurs here. That's the only place it occurs. And so we can write that pi sub r, which is the same as the derivative of the time derivative of the derivative of the Lagrangian with respect to r dot, that's just equal to not 1/2, m r dot. Derivative of L with respect to r dot is just mr dot. All right, so not too surprisingly, the radial component of the momentum is nothing but the mass times the radial component of velocity. Not too surprising. And then our equation of motion becomes d by dt of this. Well, d by dt of this, that's just mr double dot, the second time derivative of r. We assume the mass is constant. So the first term, d by dt of pi sub r, is just mr double dot, and that has to equal partial of L with respect to r. Now, there are two contributions to that. R appears in two places. One is it appears in U. That's not surprising. But the other is that it appears multiplying theta dot squared. Let's do the theta dot squared term first. Partial of L with respect to r is m over 2. We're differentiating m over 2 times r squared times theta dot squared. We're differentiating it with respect to r. All right, so that's m r theta dot squared. Do I have that right? m r theta dot squared. That's one term, but then the other term comes from differentiating u with respect to r, and that's minus du by dr. All right, let's erase this intermediate expression here and just look now at the equation for r. What does it have? Well, first of all, it has mass times radial component of a kind of acceleration here, r double dot. But then it has, first of all, over here, the force, the u by dr, but then it has this extra term. This extra term depends on the fact that the particle is moving in the theta direction. In other words, it depends on the fact that there's angular velocity, mr theta dot squared, proportional to the square of theta dot. First of all, it's positive. It looks like it's an extra contribution to the force. We can kind of think of it as an extra contribution to the radial component of force. It enters into the equation on the right-hand side as if there were a positive force. What does a positive force mean? A positive force means one radially outward. So this force, it's not a real force. What's its name? I called it Coriolis last time because I was tired. What's the right name for it? Centrifugal. This is the centrifugal force on the particle, which has the apparent effect of creating a repulsion away from the center. We're all familiar with it, right? And here's its mathematical origin. It comes from differentiating L with respect to R, but the piece of it which multiplies theta dot squared. So we don't have to. The Lagrangian method is a mindless method. It requires zero intelligence. You just follow the steps. Write down L, write down dl by dq dot, differentiate it with respect to time, and set it equal to dl by dq. You don't have to think very deeply. What's that? We have to do pi theta? Yeah, we'll have to do theta too. We've only done r up till now, yes.
What do you really mean when you say it's not a real force?
Well, by definition, I constantly say this over and over again, but then I slip into the same pattern. I'm always telling young physicists and old physicists, get rid of the word real and really and actually and really and all those words. Nothing. I didn't mean anything. It's on the right-hand side of the, it's on the right-hand side of the equation. There it is.
What is it you used to mean for years?
What I simply meant is it doesn't come from the derivative of the potential energy. That's all. All right. It is part of what is called the generalized force. Okay? And I withdraw the real. Okay. What's that?
That it's a term that arises because of the choice of coordinates.
Well, yes, but nevertheless, in some sense, it's as real as anything else. Let's go on. Let's not belabor the issue of whether it's a real force. It occurs on the right-hand side of the equation. It tends to have the effect of keeping the particle away from the origin, and that's not surprising. If a particle is moving with an angular velocity, it doesn't want to pass through the origin. But here it is, centrifugal force. Okay, let's write down, as Michael said, let's write down now the equation for theta. All right, so let's figure out what pi sub theta is. Pi sub theta, let's do it over here. Pi sub theta, that's the derivative of the Lagrangian with respect to theta dot. All right, notice theta dot squared appears, so we have to differentiate theta dot squared. And the result is m over 2. Nope, the 2 goes away because theta dot squared, when we differentiate it, gets rid of the 2. M r squared theta dot. Differentiate theta dot squared, and you get twice theta dot. The 2 eats up the 2 in the kinetic energy. That's pi sub theta. Now let's write down the equation for pi sub theta. It's d by dt of pi sub theta. That's d by dt of m r squared theta dot, the whole thing. That's equal to what? That's equal to the derivative of the Lagrangian with respect to theta. dl by d theta. Well, take a look at that Lagrangian. Do you see theta in it anywhere? I don't. I see r dot, I see theta dot, but I don't see theta. The consequence, or the fact that theta doesn't appear in the Lagrangian, is a consequence in this case of the rotational invariance of the problem that I set up. Nothing depends on that angle. In particular, the potential energy doesn't depend on angle. Therefore, dl by d theta is equal to 0. In other words, rotational symmetry of the problem tells us that the right-hand side is 0. Now, I could work this out in detail, but why bother? Why bother, since I know that what this equation says is that mr squared theta dot is a constant. Let's just use it in that form. It's a constant, and that means there's a conservation law. What is this quantity called, mr squared theta dot? It's the momentum canonically conjugate to theta. But of course, it's the angular momentum. It's the angular momentum, mr squared theta dot. The symbol that's usually used for angular momentum is capital L. And so instead of fiddling around with this equation and doing something complicated with it, we can simply say that mr squared theta dot is equal to the angular momentum, which is constant. Now, how big is it? That depends on the starting point. That depends on the initial conditions. If you know the initial condition, for example, if you know r and r dot and theta dot initially, then you know the angular momentum forever after, because it doesn't change. That's not true of mr dot, pi sub r. It does change because of the force and because of the centrifugal force. But the angular momentum does not change. It's constant, and that's what the equation of motion says. So again, this is an example of a symmetry telling us that there's a conservation law. And once we know it, we can treat L as a constant. All right? A constant which is given to us by the initial conditions. For example, that now means, let's come over to this half of the blackboard. That allows us to solve for theta dot, and it's equal to the angular momentum divided by mr squared. Well, that's interesting. Now we can come back to the equation for r. Let's come back to the equation for r. Now that we know something about theta dot, let's plug it into the equation for r. And what do we get? We get an equation for r which is mr double dot is equal. Now let me first begin writing minus du dr. Minus du dr. That's, of course, the familiar piece. And then, let's work it out, plus mr, and now theta dot squared. Where's theta dot? Here it is, right here. L squared divided by m squared r to the fourth. I've squared theta dot. That gives me L squared divided by m squared r to the fourth. Let's cancel out the unnecessary symbols. M cancels against m squared to give 1 power of m in the denominator. And r cancels against r fourth to give 3 powers of r in the denominator. R cubed. L is a constant. Once we fixed it, we fixed it. And the effect, the entire effect of the centrifugal force is now to tell us that effectively there's a force on this particle pushing it away from the origin, that's the plus sign here, proportional to 1 divided by the distance from the origin cubed, also proportional to the square of the angular momentum and also the inverse mass. Okay, so this, again, of course, this is nothing but the centrifugal force. And notice that once you know the angular momentum, once you've fixed it by knowing the initial motion of the system, then the effect of the rotational or the angular coordinate is to simply set up the centrifugal force, which is like 1 divided by the distance cubed. It gets very strong when the distance from the origin gets small. When the particle has angular momentum, it does not want to get near the origin. It's pushed away from the origin with a 1 over r cubed force. Far away, when you're far away, this 1 over r cubed gets small, and it's not so important. Yeah?
So I've already been taught that centrifugal force is actually just the effect of inertia trying to take the object in a straight line.
Is what? Is it?
Of inertia trying to take the object in a straight line. Is that not?
It is true. Of course, there are many ways to say the same thing. If a particle has some angular momentum, first of all, if it has some angular momentum, it means it has some theta dot. So that means it's not pointed, its velocity is not pointed right toward the center. If the velocity is not pointed right toward the center, then what this is telling you is, roughly speaking, yeah, it wants to move along a straight line. If it moves along a straight line, it never gets too close to the origin. But it's telling you more than that. It's telling you even a rather powerful force, unless it's strong enough to overcome this 1 over r cubed, and 1 over r cubed is very, very strong at the origin. For example, the gravitational force or the Coulomb force between charged particles is 1 over r squared. 1 over r cubed is much stronger at small distances than 1 over r squared. So this is the dominant thing at small distances. And it tells you that this particle will not crash, that the Earth will not crash into the sun as long as it has some angular momentum. Okay? Well, that's the idea of centrifugal force. And the main reason I bring it up, 2 reasons. First of all, to give you an example of how to use Lagrange's equations, the mindless application of Lagrange's equations, and to give you an example of a symmetry and how it acts to create a conserved quantity. All right, now just some, it's not really mathematics, just some notation that you'll see over and over again. Supposing you have a function of a lot of variables, and the problem is, for example, to minimize it. Sometimes, let's call the variables, let's give them a generic name, alpha sub I. I'm mixing up, I'm using lots of letters of the alphabet just to help you learn the Greek alphabet. All right, so let's suppose we have a whole bunch of, not coordinates of any particle or anything, they're just a bunch of variables. And we have some function which depends on them. The rule for finding the minimum of the function is that the derivative of f with respect to all of the alphas should be equal to 0. Sometimes you'll see that stated as delta f equals 0. Sometimes I'm going to state things in that form. Let me tell you what that means. Delta f means, it means that if you're at the minimum of a function, let's say the minimum is over here. If you happen to be at the minimum, then a small change in alpha, let's move a small change in all of the alphas. You move from one point to another. This little displacement is just delta alpha, let's call it. Delta alpha 1, delta alpha 2, delta alpha all of them. What delta alpha equals 0 says is that if you move away from the minimum, the function doesn't change to first order in small variables. Right? How do we see that? Well, if we calculate the small change in a function as we move from a point alpha to a point alpha plus delta alpha, what happens to the function? The change in the function is the derivative of f with respect to alpha I times delta alpha I, summed over I. In other words, as you move from one point to another, you get a contribution from each one of the partial derivatives. If you change the arguments of a function, the function changes to first order, ignoring things of order alpha squared, alpha cubed, and so forth, which are much smaller than delta alpha, ignoring things of scale delta alpha squared, delta alpha cubed, and so forth. The change in the function to first order is just a derivative of f with respect to alpha times the change in alpha. summed over all of the variables. Okay? To say that delta f is equal to 0 for any delta alpha, no matter which way you move, is the same as saying that all of these partial derivatives are equal to 0. The only way that this can be equal to 0 for all possible variations, the delta alphas are called the variation of alpha. For all possible variations, in other words, no matter what direction in this space you move, to say that you're at a minimum, to say that f doesn't change except to higher order, is the same as saying df by d alpha is equal to 0 for each one of the alpha i's. Okay? So these say the same thing, that derivative of f with respect to alpha for all alphas equals 0 is the same thing as saying that the variation of f is equal to 0 when you change alpha a little bit. This is shorthand for the collection of these equations over here. Variation, one says the variation of f is equal to 0. As an example, we studied the principle of least action. Here's a trajectory. And what we wrote was that the action is a minimum with respect to any variation. And one way of writing that is just to say that the change in the action with respect to a small change in the trajectory, make a small change in the trajectory, the variation of the action is equal to 0. That's another way of saying that the action is a minimum with respect to variations of the trajectory away from the actual trajectory. That's just a notational notation. Okay, now we want to get to the heart of tonight's lecture, which is the connection between symmetries and conservation laws. We talked about it a bit up till now. I gave you the examples of rotational symmetry, which we'll do in greater depth, translational symmetry, but there can be other more complex symmetries, which I won't be very specific about, but will be more general. All right, let's erase this blackboard and the idea of a symmetry is a change that you can make in the system that doesn't affect the action. For example, if we have some system of particles moving around and the particles are interacting with each other but not interacting with some external object, then if we take the whole system, including its entire motion, and we replace it by a corresponding system that's been shifted a little bit, shifted over by a small amount, small or large for that matter, then the action won't change. Why? Because the action doesn't depend on the location of the individual objects, but only their relative location. That's an assumption, of course. But more than an assumption, it defines the notion of symmetry under translation, that the action doesn't change when you translate the system. Another example is pick an origin and rotate everything relative to that origin. By the same angle, move all the particles by the same angle, start the system over. Again, the action for a given trajectory, if we displace the entire trajectory, will not change as a consequence, under the assumption, or as a consequence of the idea that the system is invariant under rotational transformations. Okay? So basically, a symmetry is an operation that you can do on a system, a change that you can make in the coordinates that doesn't affect the action. And in particular, I'm interested in a kind of symmetry which is called an infinitesimal symmetry, a small change in a system. You can build any change out of small changes. For example, if I want to rotate a system by 180 degrees, I can think of it as being built up by a lot of little transformations, each of which is a rotation by a small angle. Another possibility is translation, where if I want to say that a system is invariant under being translated by a meter, I can say it's invariant under an operation of translating it by a centimeter, but do it 100 times. Okay? So it's sufficient in most cases to understand the effect of small transformations, transformations which only displace a system a little bit. In other words, working to first order in small quantities. All right, so let's define now, first of all, a transformation on a system. It's a change in the coordinates. Under a transformation, coordinates, let's say q sub I, change to q sub I plus something small. Let epsilon be a small number times some function I of q. When I say f sub I of q, I mean that f sub I can depend on all of the q's. Right? It's a little displacement of the system. If here is your configuration space, q1, q2, so forth, then wherever you happen to be, the transformation defines a little displacement to a new location. That displacement in general can depend on where you are, where you start. But it's a small transformation. Small in the sense that epsilon is a small quantity, and we'll keep track of things to order epsilon. All right, so it's a displacement of the system, but not necessarily a displacement along an axis. Some more complicated kind of displacement. A rotation would be an example. A rotation, in the case of a rotation, if I were to just use x and y, the change in x will depend on where you are. For example, the change in x over here is different than the change in x over here and over here if the transformation is a rotation. If we're rotating the system, then the change in x, which is positive over here and negative over here, depends on where you are. But a well-defined notion of a small displacement of a system where the displacement of each coordinate depends in some specific way on all of the coordinates. So this is a collection of functions, one for each direction. And what does it mean to say that we have a symmetry? The statement of symmetry is that if we do such a transformation to the system, that the action of a trajectory doesn't change. All right? The action of a trajectory doesn't change if every coordinate is displaced in exactly this way. That's the meaning of the term symmetry. What are the consequences of a symmetry? What? Which part of it?
Your definition of symmetry with a small change in...
All right. A symmetry is a transformation which takes the coordinates of a system and displaces them a little bit depending on where you began. All right? I'll give you some examples. All right, why don't we do an example? Let's take the case of a rotation, but not working with angle and radius, but with x and y. Supposing here's the initial location of a particle, x and y. And now I rotate about the center here. I take every particle, wherever it happens to be, whatever its x and y are, and I rotate it a little bit. That changes every x and every y. But in particular, if there's just one particle, let's start with one particle. What is the change in x and what is the change in y? I'm going to write them down. You can check this. It takes a little bit of trigonometry. I may even work it out later tonight. I hadn't planned to do it right now, but just as an example. The change in x, here's x. Now, I'm going to rotate the system by a little angle epsilon, a small angle epsilon. In this case, epsilon is just a small angle. What happens to x if you change the angle a little bit? Well, I'll tell you. It changes by something which depends on y. The change in x is the angle epsilon times y. Let's see if we can see why that's true. It's easy to see in certain limiting situations. For example, if the starting point is on the x-axis over here, what is the change in x when you change the angle a little bit? 0. 0 to first order in epsilon. Right? If you change it a little bit and you're on the axis here, x doesn't change. All right, that's in agreement with this formula. On the axis means y is equal to 0. Delta x is equal to minus epsilon times y. On the other hand, supposing y is up here. Supposing we start up here. All right? Then what happens under a small rotation? We get shifted by an amount proportional to the angle. So when y is not equal to 0, x changes. On the other hand, y doesn't change at this point. So delta y, anybody know what delta y is? Somebody want to guess? Well, no, it depends on where you are. I mean, if you're in an arbitrary place. Epsilon x. For example, if you're at this point over here where x is positive, then the change in y is positive. All right, here's an example where the change in a coordinate, this could be called delta q, is proportional to the small number epsilon times something which depends on the coordinates. In this case, we would write, what would we write? We would write that f sub x is equal to minus y, and f sub y is equal to x. That would be an example. There are more complicated transformations that you can imagine besides just rotations and translations. We may get to some, but not right now. But they all have the form that the coordinates of a system change by a small amount proportional to some specific function, a different one for each one of the coordinates. Okay, that's the notion of a transformation. A symmetry is a transformation or a class of transformations such as this for which the action doesn't depend or doesn't change whenever you do such a transformation. If you like, it's a little displacement of the system or the coordinates of a system which don't change the action. Let's prove that there's a conserved quantity whenever there's a symmetry. That's our goal. Right. What doesn't?
Craps, the game.
The game. Craps?
Craps doesn't have rotational symmetry because
Dice, craps, yes.
rotating a die changes the action.
Well, it does indeed. In many ways. Yep. If you didn't put any numbers on the dice, you just made a cube, you would say that a cube has a symmetry, but the symmetry that the cube has is a discrete symmetry. You can rotate it by 90 degrees along any axis. That is not of this form. That is not of this form. You can't build up 90-degree rotations by other 90-degree rotations. You can build them up under little rotations, but the cube doesn't have invariance under small rotations. A sphere does. A sphere doesn't change when you rotate it even a little bit, and so you can build up big rotations of the sphere by lots of little symmetries, whereas the cube has what is called cubic symmetry, which cannot be built up out of little tiny infinitesimal transformations. We're interested in these ones which are built up out of little transformations. Okay, let's come to the action principle and see what the action principle tells us when there's a symmetry. First of all, let's begin with a trajectory connecting a pair of points. Vertical axis is time. The horizontal axis is a stand-in for all of the coordinates. I won't try to draw them all. And the trajectory is a trajectory of the coordinates with time. Let's first of all suppose that the trajectory that we start with is a solution of the equations of motion. That means that the variation of the action is equal to 0 with respect to all changes of this trajectory, but not quite all changes, but all changes which don't displace the endpoints. Okay? Now I'm going to make a change in the trajectory which does displace the endpoints. What I'm going to do is I'm going to apply the symmetry operation to the trajectory. If the symmetry operation is translation in space, it's just going to take this trajectory and translate it in space. If it's rotations, it's going to rotate the trajectory about some axis. Whatever it does, it moves each point along the trajectory by amount epsilon times f of q. All right, so I'll just draw that by drawing a little arrow here, displacing the trajectory depending on where the... And so it takes you to some new trajectory. The symmetry operation takes you to a new trajectory. And in general, the new trajectory will not pass through the old endpoints. The old endpoints will also get displaced by the symmetry operation. For example, as I said, if the symmetry operation is just to translate in space, then the endpoints get translated. So what we're doing is we're making a little variation of the trajectory, but not an allowable one from the point of view of the principle of least action. Okay? What is the change of the action when we do this? 0. Why is it 0? Not because of the principle of least action, but because I've said this is a symmetry. I've specified that this is a transformation which doesn't change the action. Right? But it is not a displacement which the principle of least action tells us doesn't change the action. It's the symmetry which tells us. All right, let's calculate the change in the action. Oh. We're not doing parallel transport at the moment. Later on, we'll maybe even tonight. Well, I doubt it. I don't think we'll get to it tonight. But wow, that was fast tonight. It's almost 9 o'clock.
The lecture was half over.
What?
The lecture was half over when we started.
We're going to get to time translation symmetry in a little while. Time translation symmetry says you're going to spend the rest of eternity sitting here listening to me forever and ever.
Is that a rotational symmetry?
That's hell. All right, so all right. Now, the variation of A going from the black trajectory to the red trajectory is 0 because it's a symmetry. Let's calculate by the standard method the change in the action. The standard method is what we did when we worked out the principle of least action. We said, first of all, the action is the integral of L dt. That's the action. And we said the change in the action is equal to the integral, the change in the Lagrangian when we change each one of the coordinates q sub I, times delta q sub I. That's this. Epsilon. Well, let's just write, let's see, which way do I want to write it? I guess we can just write delta q sub I. But here is delta q sub I right here. Okay, and then what else? The second term is the change in the Lagrangian when we change the velocities times delta q sub I dot. What did we do next when we did the principle of least action? We integrated this term by parts, right, so as to get rid of the time derivative over here. Right. What did that do? It changed the sign of this term put the time derivative on dl by dq dot, d by dt, and took the time derivative away from here, so that both terms multiply delta q sub I. In other words, we could put a bracket around it and bracket off the delta q sub I. But this is not necessarily the right answer, because in this case, we've also displaced the endpoints. There's an endpoint contribution coming from the integration by parts. The endpoint contribution happens now because delta q sub I is not 0 at the endpoints. So we're doing a variation which is not a legal variation from the point of view of the least action, but nothing to prevent us from doing it. All we have to do is add back in the extra term. Does anybody remember what the extra term is? It's dl by dq sub I dot times delta q, the difference evaluated at the two endpoints, t1, t2, and t1. In other words, it's the difference of this quantity at t2 and at t1. It's a difference. Keep in mind it's a difference of the quantity at 2 points. This is the full change in the action when you displace the trajectory, including a displacement of the endpoints. Now, remember that this first trajectory that we started with is a solution of the equations of motion, by assumption. We start with a solution of the equations. In other words, we start with a trajectory which does satisfy the principle of least action, or which satisfies the Euler-Lagrange equations. What are the Euler-Lagrange equations? The Euler-Lagrange equations are just that this is equal to 0. The thing inside the bracket here is just equal to 0 by virtue of the starting trajectory being a solution of the equations of motion. So that means that this whole term here can be ignored. It's 0. On the other hand, because we have a symmetry, and only because we have a symmetry, the variation of the action is equal to 0. What does that tell us? That tells us that this must be equal to 0. On the one hand, let's go through it again. On the one hand, the statement that we have a symmetry tells us that the variation of A is equal to 0. On the other hand, the Euler-Lagrange equations for the initial trajectory tell us that the thing in brackets here is equal to 0. The result is that this term must also be equal to 0. But this term is the difference between two quantities at two different times. To say that that the difference between a quantity at two different times is 0 is the same as saying that the quantity is conserved. Okay? So we immediately read off from this a conservation law. If we start with a symmetry, then, oh, incidentally, nobody has asked me about it. Perhaps I don't need to be asked about it. I have imagined summing over the coordinates. When I write that delta A is the derivative of L with respect to q sub I times delta q sub I mean summed over all coordinates. Okay? So this quantity over here is the sum over all the coordinates. dl by dq sub I dot times delta q. That's the conserved quantity. That's the conserved quantity which is conserved by virtue of the fact that delta q is a symmetry. Okay, so let's write it down now. The conserved quantity is dl by dq sub I dot times epsilon, let's put epsilon out here, times f sub I of q. Well, if this is conserved, we can get rid of the epsilon. If the time rate of change of something is 0, it's 0 with or without that constant epsilon in front of it. So if something is constant, it doesn't change whether it's constant if you multiply it by epsilon. And so epsilon was just a small number that kept track of the smallness of this term. But what we've discovered is that as a consequence of the symmetry under this particular displacement, a quantity is conserved, and that quantity is dl by dq dot times f sub I of q. In other words, the time derivative of this is equal to 0. We derived it in a slightly different form. We derived it by saying it's the same, this quantity is the same at the two endpoints. But if it's the same for every pair of endpoints, it means it just doesn't change with time. Yes, so sum over I. Sum over I. I'm going to leave, yeah, all right, sum on I. Well, that's interesting. We've now found a connection, fundamental connection, between symmetries, the principle of least action, and conserved quantities. You'll often hear things like momentum is conserved because of translation invariance, or angular momentum is conserved because of angular rotational invariance. Yes, that's true, but not every equation which is translation invariant has a symmetry that goes along with it. It is necessary, or at least sufficient, that the equation is derived from a principle of least action. We can certainly write down equations which are translation invariant but which don't have conserved quantities associated with them. They simply are not derived from a principle of least action. So it's the two things together, symmetry plus the assumption that the equations are derived from a principle of least action, that lead to the conservation law. All right, here is a quantity. I can write this another way. What is dl by dq dot? There's another name. Pi, the canonical momentum. We can write this in so many ways, but let's write it in another way. This is pi sub I times, if you like, just delta q sub I. Delta q sub I, that'll include the epsilon. We can throw away the epsilon out of it. It's still conserved. So pi sub I, or pi sub I times f sub I, same thing. Pi sub I times f sub I of q is conserved. In fact, it has a name. Pi sub I, q sub I is called the Noether charge. Noether, N-O-E-T-H-E-R. Noether was a 19th century, early 20th century, 19th or 20th. Emmy Noether. She died in the 50s? Well, she was late 19th century, early 20th century. It must have been the 20th century. I'm not sure when she discovered this theorem. But in any case, this is Noether's theorem that there's a conserved charge. Why is it called a charge? It's called a charge just by analogy with electric charge. Electric charge is conserved. And physicists fall into the habit of calling anything which is conserved a charge. But all it means is a conserved quantity. Momentum is a charge. Energy is a charge. And anything which is conserved is sometimes referred to as a charge. Then it gets complicated because sometimes we'll speak about the charge not being conserved and so forth and so on. But it's, in any case, this quantity is called the Noether charge associated with this particular symmetry. Yes, 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 summation. Summation over I. Let's work out an example or two. The examples that we'll work out are the familiar ones that we've done up till now, translation and rotation symmetry, just to see how it works. Let's suppose we have a whole bunch of particles, and the whole bunch of particles is invariant. The action, the Lagrangian, everything about this particle about the system is invariant if we translate it. Of course, keep in mind, we have to translate the whole thing. If we translate one part relative to the other, then it's not invariant because there may be forces between, for example, if there are forces between this group and this group, and we move the lower group, then of course we don't have an invariance. It's only moving all of them that in general defines a symmetry. Right. What is the symmetry? Well, there are several symmetries. there's one for each direction of space that we can translate in. But let's pick one. Let's move along the x-axis. All right? Then each particle, I'm going to write delta x sub I. I now labels the particles. I equals particle label. If there are 100 particles, then I goes from 1 to 100. It does not label the directions of space. The directions of space are just x, y, and z. So delta x sub I means the change in the coordinate, the x coordinate of the ith particle. And that's just epsilon. They all move together by an amount epsilon. All of them. And furthermore, it doesn't depend on where you are. You just translate by amount epsilon wherever you happen to be. Same amount, always the same. All right? What about, for this particular symmetry, what about delta y sub I? 0. Of course, we may also have a symmetry for moving along the y-axis, but it would be a different symmetry. So for this symmetry, it's 0. Delta z sub I also equal to 0. Or another way to say it is that the f's, all of the f's associated with the x direction are equal to 1. F is equal to 1 if it corresponds to the x coordinate of the ith particle. They're all equal to 1. How about for the yth particle? The f's are, for the y direction, they're all equal to 0. Now let's calculate the Noether charge. All right? The Noether charge is, we sum over all of the particles, sum over I, of the canonical momentum conjugate to the x coordinate times delta x, or times f times f, which is just 1. Now, it's just sum of pi sub x. What is pi sub x if the Lagrangian is just the usual Lagrangian, 1/2 mv squared, plus forces between the particles and so forth? What is the canonical momentum conjugate to x for each particle? mx dot, just the usual momentum. All right, so this is just summation of m sub I, x sub I dot. That's the Noether charge for translation along the x-axis. Just the total momentum, the component along the x-axis. Notice we didn't have to know anything specific about the forces, only that the force doesn't change if you move the whole system. That none of the forces change, or none of the, even weaker than that, the potential energy does not change if you move all the particles simultaneously. Now this, of course, would be false if there was another big heavy object out here exerting forces on all these particles. But if we're talking about a closed, isolated system, then typically a closed, isolated system, the energy will not change, or the potential energy will not change if you move the whole system. So we've derived just from the assumption of invariance under translating the system, we've derived the conservation of momentum. 1/2 m sub I x sub I dot. Of course, the same would be true for the y component of momentum and the z component of momentum. Let's work out the expression for angular momentum. We worked it out in polar coordinates, but now I want to work it out in Cartesian coordinates, x and y. For simplicity, let's just take a particle moving again in the blackboard, x and y, that's all. But let's use x and y and not r and theta. All right. So our particle, or it could be a collection of particles, but let's start with one particle. It's coordinatized by an x and a y. Those are our two coordinates. Q are just x and y. If there are many particles, then it's many x's and y's. Okay? And what is the transformation we're talking about? The transformation we're talking about is simply the rotation of the location of each particle relative to the origin by an amount proportional to epsilon. Right? A while back, I wrote down what the transformation is like, what the mathematical rule is for the rotation. I'll write it down again for you. Delta x is equal to the small angle epsilon times y, and delta y is equal to epsilon times x. Now, you can work this out using a little bit of trigonometry. If you start with a point in the xy plane and you rotate the xy plane, everything in the xy plane by a small angle, then you can check that the components of that particle or that point change in this manner here. It's hardly even trigonometry, it's even simpler than that, but it's easy to do using a bit of trigonometry. I will simply write down the formula. Delta x is minus epsilon times y, delta y is epsilon times x. If epsilon is a positive number, then it corresponds to a rotation of the system counterclockwise. If epsilon is negative, it corresponds to a rotation of the system clockwise. Okay, so epsilon has to be what?
In radians?
Yeah, epsilon, good. Epsilon is measured in radians. Thank you. Yeah, not in angle, not in, what are those other units? Degrees. Yeah, right. Epsilon in radians. Right. But in fact, if it wouldn't really matter, because if I'd done it in radians, then there would just be another factor here. It would just change epsilon. It would change epsilon and multiply it by some number. Okay, 60 or some 57 point something, I forget what. So the formula would be the same, except epsilon, instead of being epsilon, would be some number times epsilon. Okay. All right, so what then, this is what we would call then epsilon times fx, and this is what we would call epsilon times fy. The change in x is epsilon times fx, and the change in y is epsilon times fy. We read off from that fx is equal to minus y, and fy is equal to x. Now let's work out the Noether charge. The Noether charge, where did we have it? Here it is, right here. Let's work it out. It's the sum over the two coordinates of pi x, that's just the x component of momentum, times fx, but fx is minus y. So that's minus, in fact, let's just call this px. Standard notation for ordinary linear momentum. Momentum along the x-axis minus px times y. The minus sign comes from this minus sign over here. And the other one is plus py times x. Py times x minus xpy. That's pi times f sub I summed over the two coordinates. Right? xpy minus ypx. That's the angular momentum. It's the thing which is conserved by virtue of rotational invariance. If there are many particles, then there's a contribution of this for each particle. Summation over all the particles. Right? Again, we didn't have to know very much about the forces between particles. We didn't have to know very much about the details. All we needed to know is that the action doesn't change when we rotate the system about an axis. This is undoubtedly familiar to many of you. This is basically the z component of r cross p, but we'll come back to that later. It's the z component of the cross product of the radius vector and the momentum vector. And there is, of course, a component of the angular momentum for any direction that you might rotate about. This corresponded to rotating about a direction perpendicular to the blackboard. If I had some collection of particles, I could have rotated about any axis, and I would have a whole vector's worth of angular momenta. But for our purposes now, the simple thing, the angular momentum of a particle moving in the blackboard, xpy minus ypx, is just an inertia charge associated with the rotation. All right, so it's not, again, once you know Noether's theorem, it's a mindless exercise to calculate the conserved quantity. Of course, what is not necessarily mindless is looking at a system and figuring out what all its symmetries are. That can sometimes be hard. But once you've located a candidate for a symmetry, you then check, does the Lagrangian change when you do that transformation? If not, then you go through the mindless exercise of calculating the inertia charge, and you've discovered a conserved quantity. So for example, if you have the Earth moving around the sun, and you start the Earth at 11 o'clock exactly, moving in this direction with a certain velocity, it'll orbit the sun and do whatever it does. If you started the Earth instead of at 11 o'clock, you started it at 11:01, then it'll trace exactly the same path, always 1 minute behind the previous trajectory, and will define exactly the same trajectory except displaced in time by that 1 second. Now, what's the assumption is that nothing in the laws of physics or in the problem that you're doing depends explicitly on time. You can imagine situations where things do depend explicitly on time. For example, again, it usually has to do with looking at parts of a system. But if our system happened to be a pair of objects, and off over here on the side was a big heavy planet, which I'm not going to bother thinking of as part of the dynamical system, but it happens to be moving in some way, some specified way, then the forces on these objects will be explicitly dependent on time. They'll be explicitly dependent on time through the motion of this big heavy object, which we're not taking into account in our equations of motion. We take it into account simply by saying the forces are time dependent. In that situation, if we start these two guys here at a slightly different time, we'll get a different answer. Why? Because the big heavy planet here will be in a different place. But if we take a closed system not subject to any kind of influences which are time dependent, then these kind of systems typically have a translation invariance under time translation. In other words, change all the times in the problem by the same amount, by that same 1 second or that same epsilon, and a trajectory changed in that way will stay a solution of the equations of motion. That's called time translation invariance, and we can draw pictures to illustrate it, and we can write equations to illustrate what it means, and then we can try to find the consequences of those equations. So let's suppose again that we have a solution of equations of motion which we represent by a trajectory, q's as functions of time. Now, let's move the trajectory forward in time. Vertical is time, and let's move it forward in time by the amount of epsilon. That means we take every point on the trajectory and move it by the same amount epsilon. It gets a little tricky over here because, well, you can see what happens. Notice that the endpoints also will move, because the endpoints are at some particular time. But let's just move the trajectory, and it'll move to something that looks like this. It's just been pushed up by amount epsilon. All right, so t has gone to t plus epsilon, if you like. What is the transformation on q? Every q changes. Notice what happened. All right, there's two ways to think about it. We can think of this as a change of the trajectory by moving every point forward in time, but we can also focus on a particular time. If we focus on a particular time, we see that the trajectory has moved, in this case, to the left over here and to the right over here. So we can think of it in two ways. We can think of it as the trajectory being moved up, or we can also think of it as the trajectory having been displaced horizontally, but the horizontal displacement is not fixed. It depends on where you are along the trajectory. Okay? Let's think of it in the horizontal way. What happens to q at each instant of time? Right? Q of t goes to q of t minus epsilon. Epsilon is this fixed amount that you've shifted the trajectory. Why is it minus? Let's come to it. It's actually minus and not plus. We'll see why in a minute. So whatever the trajectory was, q of t, plug in t minus epsilon instead of t, and that's a new trajectory which is displaced in time by amount epsilon. If you doubt that the sign here, we'll see why it is, as I said, in a moment. What is the change in q? The change in q at the instant t is equal to the derivative of q with respect to t times minus epsilon. If I displace a function by a small amount in the argument, then the change in the function is just the derivative of the function with respect to t times the change in t. And there's a minus sign here because I put a minus sign here. Now, do you doubt the minus sign? Let me show you why the minus sign is there. Supposing, for example, notice, first of all, that what it says is that the change in q, the little displacement, is proportional to the time derivative of q. If there was no time derivative, that would mean that the trajectory was perfectly vertical. If the trajectory was perfectly vertical, then there would be no time derivative. dq dt would be equal to 0, and shifting the trajectory up and down would not shift it horizontally at all. So the fact that there's a horizontal shift is because there's a velocity, because the trajectory is tilted, if you like. Let's suppose the trajectory is tilted this way, okay? And let's move it upward. Let's push the trajectory upward in time. All right, so let's let the horizontal axis be q. The vertical axis is time, and I've pushed the trajectory forward in time. Which way has it moved in q? Negative. So a positive q dot is positive, a positive q dot shifts the trajectory backward. That's what this minus sign is doing here. A positive q dot means that the trajectory shifts backward. I always get confused by this sign, and that's the way I have to think about it. I have to draw a picture and say if q dot is positive, obviously this corresponds to q dot, q increasing is time increasing, then pushing the trajectory forward in time actually pushes it back in q. So delta q is minus q dot.
Or the other way to think of it, I think, is that if you're changing t to t prime,
P to P prime?
t to t
T prime, yeah.
where t prime is further ahead in time,
Yes.
you could get back the original.
Yeah.
prime.
Yeah, you could, right. I draw the picture and I see it this way. Other people can see it different ways. All right, so that's delta q. Now let me draw the picture. Let me draw the picture a little more clearly, and then work out the consequences of a symmetry. So here's our trajectory. Let's say it looks like that. Our initial trajectory. It's assumed to be a solution of the equations of motion. Now let's push it upward in time to become this trajectory over here. But let's continue it back a little bit. The trajectory could be continued back a little bit so that it matches this point over here. Well, actually that's not necessary. That's it. That's the trajectory. Okay. What do we know about this new red trajectory which has just been shifted in time? We know first of all that it's still a solution of the equations of motion. Why? Because we've assumed that we have a symmetry on the time translation. That's number one. What does that tell us? That tells us that the action of the new trajectory must be the same as the action of the previous trajectory. That's what it means to have a symmetry, that the action doesn't change if we shift the trajectory forward in time like this. Let's write that down. Oh, before we do, let's break up the trajectories into three pieces. Let's see, how do I want to do this? Yeah, all right. Let's break off a piece over here. Since this trajectory, the red trajectory, begins at this point, let's chop off this little piece of the black trajectory. We're not going to chop it off, but we're going to wind up treating it slightly separately from the rest. And since the black trajectory ends over here, let's chop off a piece of the red trajectory over here. As I said, we're not going to chop it off, really. We're going to take them into account, these extra pieces. But for the moment, let's chop them off and then add back in the contribution to the action from the extra little pieces here. All right. Now, notice what delta Q is. Delta Q is this displacement over here. Let's write down the total change in the action from the black trajectory to the red trajectory, the full trajectories. The change in the action is equal to 0. Why? Because I've assumed time translation invariance. On the other hand, we can also write it down explicitly. The integral . All right. First, we'll take the contribution . Let's call it from TA to TB over here. In other words, let's neglect these little extra terms coming from the endpoints here. One black extra piece and one red extra piece. All right. The first contribution comes from the region between TA and TB. And that's equal to the derivative of the Lagrangian with respect to Q times delta Q. But what is delta Q? That's minus Q dot times epsilon. And what's the second piece? The second piece is, we can just call this delta Q. The second piece is plus the L by dq dot times delta Q dot. And delta Q dot we can get by differentiating this expression over here. It doesn't matter what it is. It's just the usual thing. The difference between the action along the red piece of the trajectory and the black piece of the trajectory is just, first of all, this expression over here. All right. Then there's the contributions coming from integrating by parts. And I'm getting tired, as you can see. I get tired about this time of night and I get sloppy. Okay, here's what we have up till now. Now we have two extra pieces. The red extra piece over here and the black extra piece over here. Let's give them names, A and B. All right. Plus A minus B. They're just names for the moment. Okay, what do we do with this? What we do with this is the usual thing. We integrate it by parts. We integrate it by parts, and that gives us the first term, which is integral dq, the usual thing, dl by dq minus d by dt of dl by dq dot, all times delta q. Let's not even write down what delta q is. That's the first thing.
That should be, those should be.
Ah, sorry, dt. All right, the usual thing. Good. All right. Now, what have I left out? I've left out, first of all, the contribution I got by integrating by parts. All right? So that gives me plus q dot, or sorry, plus delta q times dl by dq dot evaluated at tb minus at ta. Okay. But then I've left out these extra little contributions coming from here and from here. I'm interested in the difference of the action on the red trajectory and the black trajectory. That's why I subtracted A and B. The red trajectory has a little bit of extra over here called A, and the black trajectory has a little bit of extra over here called B. If I'm interested in the difference between the action of the two trajectories, I want to subtract A and B. All right? So we have plus A minus B. And we'll work out in a minute what A and B are, but whatever they are, they're the little pieces coming from the overhangs because the time intervals don't begin and end at the same time. What's in here? What's in here is 0. Why is it 0? Because the black trajectory satisfies the equations of motion. Right? The black trajectory satisfies the equations of motion, and this is just the equation of motion. In other words, setting this equal to 0 is what tells us that the black trajectory is equal to a solution of the equations of motion. So this is 0. What is the total change in the action? 0, because we have a symmetry. So exactly the same as before, we can neglect this, and we get the contribution from the endpoints, the difference of A and B, the difference of the endpoints, plus this extra thing over here that we didn't see previously. This contribution is exactly the same as in the Noether theorem that we studied before. All right? The contribution coming from integrating by parts because delta q is not equal to 0 at the endpoints. Over here and over here, delta q is not equal to 0. But now we get this extra contribution over here. Right. What is delta q? Delta q is minus epsilon times q dot. So we can put a minus sign here and epsilon times q dot. Where did the q dot come from? The q dot came from the fact that the variation in q is proportional to q dot. Plus A minus B. All right, now what are A and B? I don't know whether you recognize this or not. This is a contribution to the energy, but we'll come back to it. Leave it for the moment. What is A and B? Let's look at A. A is this overhang piece over here, the red trajectory. The red trajectory continues after the black trajectory ends. Black trajectory ends. The red trajectory goes on for a little bit of time. How much time does the red trajectory go on for? Epsilon. We've shifted the trajectory ahead by a time epsilon. So it goes on for time epsilon. What's the extra action on this little segment of the trajectory over here? Well, what is the action? The action is the integral of L dt. Right? The Lagrangian along here doesn't vary much between here and here. Why not? This epsilon is a very small time interval. Imagine epsilon is an extremely small time interval now. That means this trajectory doesn't move very much from here to here. If we make epsilon really, really small, then it goes from here to here. So the coordinates in this extra little piece here don't change very much. They're practically at a single point at this point here. So that means we can write down for the Lagrangian just a Lagrangian at this endpoint here. It's just a Lagrangian at the endpoint over here. Let's say at, what is that called, TB? Times the little change in time, epsilon. That's A. Again, why is it A? Because the integral of L dt over this tiny infinitesimal time difference between this point and this point, this time interval epsilon, over a sufficiently small time interval, an integral is just equal to the integrand times the time interval. So if epsilon is small enough, this little extra piece is just a Lagrangian at the endpoint times epsilon. That's A. What about at the other end? At the other end, we have exactly the same thing. B, I don't know why I'm using red and black, I'm getting confused. B is equal to, B is equal, L at TA times epsilon. No, TA over here. For some odd reason, I've called the beginning of the trajectory B and put it at TA, and the end of the trajectory A and put it at TB. No. That's life. So TB, or A, is the Lagrangian at TB at the endpoint times epsilon, and B is the Lagrangian at TA times epsilon. Where does the epsilon come from? The epsilon comes because we're doing an integral over a small amount of time. Lagrangian is just the integrand. Again, if you do an integral over a sufficiently small time interval, the answer is just the time interval epsilon times the integrand. Right? So those are the two extra end terms. So we can write them down now. We get, yeah, we're assuming nothing is singular, absolutely. We're assuming nothing is very rapidly varying, or equivalent correctly, that we can make epsilon small enough so that we can ignore the variations of the function over the interval epsilon. Okay. Sometimes you can get into trouble with such assumptions, but not here. Okay, so this is L at TB minus L at TA. In other words, times epsilon, all times epsilon. Everything gets multiplied by epsilon. And all of that is equal to 0. Why 0? Because we have a symmetry. The change in the action, in other words, this change in the action is simply equal to the term that we get from the integration by parts plus this little overhang region here. And this is it. That's the difference in the action of the two trajectories. And it must be equal to 0. Everybody understand why it's equal to 0? It's equal to 0 by virtue of the assumption that we have a symmetry, that the action doesn't change when we move everything ahead a little bit. Okay, now we can see what goes on. Obviously, we have a conservation law. We have something evaluated at B. What is it? The thing that's evaluated at B is the Lagrangian minus q dot times dl by dq dot, evaluated at B, minus the same thing evaluated at A. That difference is equal to 0. There's another way of saying that is that this quantity is conserved. The Lagrangian minus the sum over I of qi dot dl by dqi is conserved. This is the kind of term that we had previously. dl by dq dot times the variation or the small change in q Now we get this extra term from the overhang regions. So we've discovered a new conservation law. Let's write down what it's a conservation of. The new conservation law involves the Lagrangian minus the sum of all the coordinates q sub I dot dl by dq sub I dot. That's pi sub I. That's the thing which is conserved because of time translation invariance. Mindlessly, all we have to do is calculate the canonical momentum for each coordinate, multiply it by the corresponding velocity, q dot, put a minus sign in, and add the Lagrangian. That's Noether's theorem for time translation invariance, that this is conserved. What is this called? Minus h. It's conserved, and if a thing is conserved, of course, so is its negative. So let's throw a minus sign in. This quantity is conserved, and it's called h, the Hamiltonian. It's also the energy. It's a conservation law that's associated with the translation of a system under time, or the symmetry under translation by time, and it's called the Hamiltonian, and it's the energy of the system. Let's work it out for a simple example to see that it really is the energy. All right, so let's work it out. Let's take 1/2 mx dot squared minus u of x. That's the Lagrangian. What's the canonical momentum conjugate to x? It's just mx dot. That's p, or that's pi. What's pi times q dot? That's just pi times x dot. Pi times x dot, the first term here, pi x dot is just equal to mx dot squared. We just multiply pi by x dot. So that's the first term here. Then we have to subtract the Lagrangian. All right, so h then is equal to, in this case, h would be mx dot squared, that's pi times x dot, minus the Lagrangian, minus the Lagrangian. The Lagrangian is mx dot squared over 2 minus u of x. All right, so one term comes from the pi q dot, that's mx dot squared, and then we subtract off the entire Lagrangian. Notice what happens. What's mx dot squared minus mx dot squared over 2? It's just mx dot squared over 2. Notice we're subtracting minus u of x. That means plus u of x. So indeed, this quantity which is conserved by virtue of the time translation invariance really is the sum of kinetic energy and potential energy. This is true very generally. If you like, even better, it's the definition of energy in mechanics. The definition of energy is the quantity which is conserved as a consequence of time translation invariance. Let's see, is it worth, perhaps we can do, well, let me take some questions at this point here, because this is a pretty slick derivation, but you may have missed some of the little steps. So let me go back, or let me field some questions at this point. Yeah.
I had a really simple question about angular momentum.
Oh, well, let's hold back on angular momentum for a minute. I want to concentrate on this derivation here. Just to go back over it schematically, we said that if we translate the trajectory in time a little bit, the action should not change. So that tells us that delta A is equal to 0. All right? then instead of thinking of translating the trajectory forward in time, we thought of it as a shift by amount q dot. Well, then we calculated the difference of action along the black trajectory and the red trajectory, subtracting off these overhang regions, forgetting the overhang regions for a minute. That gave us something which was proportional to the extra terms that we get from the integration by parts. Why? Because the endpoints of the trajectory move a little bit. We get nothing from the term that's proportional to the equations of motion. In other words, nothing that would be there if the equation of motion is satisfied on the black trajectory. So we get one contribution coming from the integration by parts end term, and another contribution coming from these overhang regions here. One of the contributions is this q dot pi. That's the contribution coming from the integration by parts endpoint contribution, and then the other term coming from the overhang here is the difference of Lagrangian at the two ends. Those two terms combined give us the conservation of the thing that I've called H.
Just above there, you got the Navier charge written out, pi FIQ.
Yeah, that was for the case, that was not for the case where we're displacing time. It's the case where we are simply shifting the coordinates.
That's how the extra L got added in.
Yeah, the extra L got added in because of the shift of time and these overhang regions.
And that was only important because the action's defined over the time.
Yeah.
That didn't occur when you were doing it all gas.
Right. When all we did was shift the trajectory, keeping the time endpoints fixed, that didn't occur. So that's the extra new thing. This thing is not new. That is just equal to delta Q times pi. That's the same as in the Noether example. The extra term comes from here, and it's because of the shift of the endpoints in time here. Okay? So it's a rather neat fact. As long as your system is time translation invariant, and assuming it comes from a principle of least action, there is always a conserved energy. And this is, in classical physics, the most general definition of energy. It's the reason why in all the systems that you've ever studied, there's always something called energy that's conserved. But ultimately, it does trace back to the principle of least action and the time translation invariance. Okay, so any other questions about this particular point before I take questions about other things? Yeah.
I'm not sure what we began with. At one time, the definition of Lagrangian contained the word energy.
No, good. Good, all right. So the did the lights go out? The definition of Lagrangian is the integrand in the action. Okay, that's the most general definition. Right? And as long as the action exists, as long as the Lagrangian exists, this is the definition of energy. If the energy happens to be of the form of a conventional kinetic energy, or if the Lagrangian happens to be of the conventional form of a kinetic energy minus a potential energy, then the Hamiltonian will be the kinetic energy plus the potential energy. Okay? So this is more general and more fundamental. For the specific example where the Lagrangian is a sum of terms of this type, a sum of many, many terms, all the particles in the world, all the different directions of space they can move in, under those circumstances, the Hamiltonian will just be your familiar kinetic plus potential energy. So as far as definitions go, from this point of view, the more fundamental quantity is Lagrangian, and the only real assumption is that it depends on the q's and the q dots. All right?
So it's up to the physicist to pull the physicist has to pull the Lagrangian out of the air, and then
He doesn't pull it out of the air, he pulls it out of experiments.
from that to the air.
Right. Now, of course, that's not really in practice what's done. In practice, what's done may be a dirtier, a more complicated procedure. But thus far, all known systems including field theory, including gravitation, all these things, general theory of relativity, special theory of relativity, they're all of this form. Yeah.
So are there any general conditions for Lagrangian function to be admissible Lagrangian?
Absolutely. There are conditions. First of all, it should be a function only of the q's and the q dots. That's one thing. And the second thing, which we'll eventually come to, which is important, is, which we haven't stated at the moment, when we calculate these pi's, they're typically functions of q and q dot. The pi is a partial of L with respect to q dot. It's important that you can solve for the q dots in terms of the pi's. But I don't want to get into that now. Yes, there are conditions which are important and define the admissible Lagrangians, absolutely. This is basically single-valuedness of the connection between velocities and canonical momenta. But we'll come to that when we, yeah.
If the trajectory,
To which?
the figure in the left hand,
This one?
if they are inclined in this direction, then will that be a positive sign there?
This case?
Yeah, if they are inclined in the not this 45 but another 135 degree, then will that be a positive sign over that equation?
I'm not understanding. Let's see. Oh, you mean if the trajectory is going, oh, do you want me to change the trajectory or change epsilon? All right, we can change epsilon. If we change the sign of epsilon, then we're moving the trajectory down. Oh.
Inclined in this direction, not this direction.
You want to change the trajectory? Yeah, all right, then we change the trajectory, it goes this way. You want to change the trajectory so it goes that way? Yeah, then q dot is negative. We're moving the trajectory forward in time, same epsilon is positive. Then q dot is negative, okay? Q dot is negative minus q dot is positive, and delta q is positive. So that says that delta q now is positive. Okay. Well, first of all, we'll do some more examples. The harmonic oscillator in particular, its Lagrangian formulation. But what I want to work into now is the Hamiltonian form of mechanics. The Hamiltonian form of mechanics is central to the connection with quantum mechanics. Now, at this point, we're sort of caught up where I want it to be. We'll get into the Hamiltonian form, but I think we should also do some more examples, some more practical examples of the utility of this and how you actually work out problems, a couple of problems. But is there anything you would like to cover at this point? Yeah.
You mentioned that you would get the Lagrangian from experiment. You could kind of do an example where you're starting with no information other than...
Well, of course, that's not really the way that it happened, of course. The way that it really happened is the equations of motion were deduced from experiment. And then they were cast into Lagrangian form by people who were interested in putting the equations into Lagrangian form. The historical evolution of physics tended to be through equations of motion. For example, Maxwell's equations have an action formulation, which I hope to get to, or the motion of a charged particle in a magnetic field has an action formulation. It's an action formulation which you probably would not have guessed very quickly. The first thing that was discovered by Lorentz at the end of the 19th century was the equation of motion, the F equals ma type equation for a particle moving in a magnetic field. And then later that was put into, it was realized that that had the form of a Lagrangian equations of motion. But ultimately, you don't pull it from out of your head. You either pull it from the equations of motion, which you try to put in Lagrangian form, or from experiment. I'm not sure what the question was.
Well, I was just wondering how you would proceed from observation to getting the Lagrangian.
Well, okay, these days, in the days of quantum field theory, the thing that you actually measure in experiments is more closely related to the Lagrangian than to the equations of motion. But, for example, particle collisions are the cross-sections for particle collisions, the events which happen, the individual events, the emission of photons and that sort of thing is directly connected with terms in the Lagrangian, directly. And so you read them off particle physics collision amplitudes or particle collision probabilities. That's not classical physics, although the same Lagrangians govern the classical limit. In classical physics, as I said, the things which were discovered first were the equations of motion. What was the history of Maxwell's equations? Well, the history of Maxwell's equations went back to Faraday and Faraday's intuitive insights into fields and so forth, and Maxwell fiddled with them until they became consistent and then discovered the wave equation for light, all that stuff. Later on, in the beginning, the early 20th century, people realized that those equations had the form of Euler-Lagrange equations for a principle of least action, and that the action was a lot simpler than the equations of motion themselves. Typically, incidentally, the action is much simpler than the equations of motion. The simplest example, let's take the particle moving in 2 dimensions. It has this complicated centrifugal form over here that would not be so easy to guess on general grounds. The equation is fairly complicated with the mr theta dot squared. You wouldn't easily guess these equations of motion. On the other hand, 1/2 mv squared plus the potential energy is very easy to remember. You write it down and then you do the Euler-Lagrange trick on it and you get the equations of motion. So from a practical point of view, it is always easier to calculate the Lagrangian first and then deduce from it the equations of motion than it is to calculate the equations of motion directly. I will eventually show you some fairly difficult examples which are very easy to think about when you think about an action. Next week, though, not now.
When did all the pieces come together historically for this formulation that you were teaching on?
Well, in mechanics, as opposed to field theory, it was Hamilton in the the later second half of the 19th century. 1860, I'm not sure exactly what year. So this is late 19th century. Lagrange was earlier. First Lagrange in the first half of the 19th century, then Hamilton in the second half. And of course, the whole thing reached its real fruition with quantum mechanics. Quantum mechanics makes very, very heavy use of the Hamiltonian form of mechanics. It really is the explanation for all of this. Okay, if there are 1 or 2 more questions, I'm reaching the end of my.
Did you say at one point like the Lagrangian can be a function of explicit function of time?
It can be. Oh, yeah. Okay, let's come back to it at the beginning of next time. But what happens if the Hamiltonian, or the Lagrangian, excuse me, is an explicit function of time, then the energy is not conserved. Why is that? Well, if the action is an explicit function of time, that means that the variation of the action when you push a trajectory forward will not be 0. A trajectory pushed forward in time will not be a solution of the equations of motion anymore. If the action explicitly depends on time, in other words, forces change with time and so forth, then the new trajectory will not have the same action as the original trajectory. If that's the case, this whole derivation breaks down and the energy is not conserved. But we'll work out, next time, remind me, the next time I'll work out what happens to the energy if the Lagrangian has an explicit time dependence in it? The answer is energy is not conserved.
The preceding program was brought to you by Stanford on iTunes U and is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at itunes.stanford.edu.